Hello and welcome. In this video, I'm going to talk about emission and excitation. Now, there's going to be light that's going to be either absorbed or emitted when atoms undergo these transformations. And we calculate the energy and wavelength and frequency of the electromagnetic radiation using something called the Rydberg equation. And you're going to learn all of that in this little talk. First of all, let me define for you what excitation is, okay? An atom is going to absorb energy, and the electron is going to be promoted to a higher orbit. So I've got the Bohr model of the atom written out here. N equals 1 is the centralmost orbit, N equals 2 is outside of that, N equals 3 is outside of that, and so on, okay? And a transition can be written N equals 1, arrow, N equals 3. So that means you have an electron in the N equals 1 jumping to the N equals 3. It doesn't have to go just to the next orbit. You can go from N equals 2 all the way to N equals 7. It's possible to hop all the way like that, okay? Now, remember that the higher the N, the higher the energy. Why is this? Well, the proton is positively charged and electron is negatively charged, okay? And if the electron is very far away from the nucleus, it's going to have a high energy, okay? Because opposite charges attract. Now, remember that the energy is proportional to -1 over n squared. So there's a little formula there. Well, the proportionality is there, okay? So let's go ahead and take a look at this. Here's an electron drawn in the N equals 1 orbit. So it's rotating around or moving or occupying that orbit, all right? In comes a beam of light or a photon. It strikes this atom, and then the electron goes from the N equals 1 and hops to the N equals 3, all right? So we call that a quantum leap. I think there was a television show in the 1980s, Quantum Leap. You might check that out. All right, what about emission? Emission is the exact opposite of this process. In emission, you actually start with an excited state atom, okay? And the atom is going to release energy. When the electron, electricity or electromagnetic radiation or heat, these are all forms of energy released by an atom. So when the atom releases that heat, the electron is demoted to a lower orbit, okay? So we can write the transition, for example, N equals 3 going to N equals 1. And keep in mind that the lower the N, the lower the energy, because electrons and positively charged protons are opposite in charge, so they like to be closer together. That's the lower energy state. All right, so let's sketch this out here. We have an electron in the N equals 3. Okay, boom. It hops to the N equals 1. And in that process, it spontaneously emits a photon of light. Now, it turns out we can calculate that wavelength of light from the Rydberg equation. That might be red light, it might be green light, it might be invisible infrared light or invisible UV light, for example. Okay, I kind of like this figure in the OpenStax chemistry textbook. It plots energy. Energy is high on this scale and energy is low at N equals 1, okay? And I have the orbit numbers on the right there by my picture. So you got N equals 1 and then N equals 2, 3, 4, 5, okay? And they've calculated the energies for all of these, okay? Now, the energy difference gives us the energy of light emitted. So if we go from N equals 5 all the way down to N equals 1, we could subtract those two energies and get the energy difference for the light or the photon that's being emitted from that process. Now, we do that with a Rydberg equation. Okay, I do not have a summary slide at the end of this, so please write this formula down. Okay, E is equal to the Rydberg constant times 1 over N1 squared minus 1 over N2 squared. Okay, now keep in mind N1 is always going to be the lower number and N2 is always going to be the higher numbered orbit. Okay, so if I'm going from 4 to 2, N1 is 2, N2 is 4 because I'm going from 4 to 2, and you want to plug in the lower number into the N1, all right? Now remember that the energy is proportional to 1 over N squared, and once you find the energy, you can go ahead and use those other formulas I've already talked about to calculate the wavelength or frequency, okay? Let's do an example. So here we want to calculate the wavelength of electromagnetic radiation released from, it looks like an emission, from N equals 5 to N equals 3, okay? So first of all, you want to identify the lower number, N1 is 3, and the higher number, N2 is 5. Plug this into your Rydberg equation. Here it is in its basic form. And plug it in. So it's 1 over 3 squared minus 1 over 5 squared. So you have some squared terms in there. So that's the Rydberg constant times 1/9 minus 1/25. When I do this on my calculator, and please pause the video and check it out for yourself, I get 1.55 times 10 to the minus 19. The superscript didn't work out well there. All right, so we have the energy, but not the wavelength. The energy is 1.55 times 10 to the minus 19 joules. We want to know what the wavelength is. So we want to use the Einstein-Planck equation, E equals h nu, right? We solve for nu, which is frequency. I know it's not wavelength yet, but it's frequency. Frequency is energy divided by Planck's constant. And you can see here how the joules cancel and the units look weird. You have divide by S. And remember, that's hertz. That's cycles per second, all right? So now we know the frequency is 2.34 times 10 to the 14th hertz. And that's a very large number, but this is common in these sorts of calculations, all right? This transition, we have an energy of 10 to the minus 19 joules. We have a frequency of 10 to the 14th cycles per second. So this is where we use the so-called speed of light equation, okay? The speed of light is equal to the wavelength times the frequency. We want wavelength, so divide both sides by nu. That gives you this formula, and you plug things in. So the speed of light is 3.00 times 10 to the 8th. Divide that by the frequency we calculated earlier, and we get a wavelength of 1.28 times 10 to the minus 6 meters. From here, you could calculate nanometers and figure out what color of light it is, or what region of the electromagnetic spectrum is it. Is it UV? Is it IR? Is it visible? Okay. So this in a nutshell gives you an idea of how to use the Rydberg equation. Thanks for watching. I hope this clarified any kind of questions you may have had. Please like, please consider subscribing, and have a great day, everybody.